Hello, I'm Cynthia Howell, and I am your moderator for the webinar series today. This is a series designed for CMI and by CMI, and I want to tell you a little bit about it before we get to introduce our presenter. So first, our hub webinars, they're hosted by Colorado School of Mines, one of our CMI hub members. And we're always looking for topics that are applicable to you and your work as our CMI body. So please don't hesitate to give us any ideas for future webinars. This is a public webinar, and it is going to be posted within about a week at aimslab.gov/CMI. And it's under the webinar menu. And also you can always find it on our YouTube channel, which is Critical Materials Innovation Hub. Questions. We're actually going to hold the questions till the end of the presentation. And at that point in time, our presenter will gather the questions and answer them. But please, when you have a question, put it in that question and answer box so we have a few queued up at the end of the presentation. And now I'd like to tell you a little bit about our presenter. Our presenter today is Dr. Magdi Azer, and Magdi brings about 20 years of technical and business management experience to his current position. He has worked in many repair, development, engineering positions at General Electric, and he brought that all to his current post, where Dr. Azer is an Associate Director for Manufacturing Science at the Illinois Applied Research Institute, University of Illinois, Urbana-Champaign. And he also is CTO of REMADE, and we're going to hear a lot more about REMADE, so I don't want to take any more of that time. I'd just like to hand it over to Magdi Azer.
Thanks, Cynthia. I appreciate the
welcome.
opportunity to come and speak today. I feel like I'm coming full circle. So when I was at GE Global Research, CMI was just getting started, and a number of my colleagues were doing work with CMI related to phosphors for lighting, looking at substitute materials for neodymium iron boride magnets. So it's nice to be back. What I'd like to do as we go through the discussion today, and we talk about how the circular economy helps us in a resource-constrained world, is I like to start with the big picture. And when I say big picture, what I mean is globally. In 2019, the Ellen MacArthur Foundation put out a report called Completing the Picture, How the Circular Economy Tackles Climate Change. And one of the things that they showed is that while it's great to have a focus on transitioning to clean energy globally and greater electrification, and I know CMI is doing a lot to support all of that work, that alone will not get us to zero emissions. That if you really want to get to zero emissions, you have to start looking at how we make products, how we produce materials, how we handle land use and land management. And so 45% of global emissions is attributed to those things. And in fact, if you look at 5 materials, food, steel, cement, plastic, and aluminum, those account for almost half of that 45%. So we have to focus on the material side as well as the transition to a clean energy technology. And of course, consistent with circular economy principles, you've got to focus on eliminating waste and pollution. So if you don't have to remake something, you don't have all of that waste. Trying to keep materials and products in use is another big focus, of course, because that allows you to retain the embodied energy. And of course, on the land side, finding ways to regenerate natural systems is important. I think it's also important to talk about resource consumption. So 2 months ago, the International Resources Panel from the United Nations Environment Program released their Global Outlook, Resources Outlook 2024, called Bend the Trend. And what they did is they looked at historically and projecting into the future, what has global material consumption looked like? And it's not a great picture. In fact, over the last 50 years, globally, we've tripled material use. That's not surprising when you look at the rise of China and many other countries that are developing and their demand for resources to fuel that development. That's a big part of it. And within sectors, 90% of that demand is going into the built environment, mobility systems, food and energy systems, infrastructure. So we're just not only consuming more and more materials, but we're doing so at an unsustainable pace. If you, I'm not sure how many of you are familiar with Earth Overshoot Day. Earth Overshoot Day measures marks the day in the year where where our consumption of materials exceeds our ability to regenerate them naturally. So I think last year it was August 2nd. In a couple of weeks, on June 5th, they'll announce where they think Earth Overshoot Day is going to be. But the bottom line is we're consuming almost twice as many resources as we have Earths. So we're on an unsustainable pace. And again, that's where the work that REMADE's doing and the circular economy come into play. So part of the way that circular economy addresses that resource consumption standpoint is, again, historically, since the beginning of the Industrial Revolution, you can track resource use and GDP globally. They track pretty well. And again, that's part of that linear take, make, waste, circular, linear economy that we've spoken about. But what we have to do is find ways to decouple our resource consumption from economic activity. So again, this resource decoupling. We also have to find ways to decouple the environmental impact of our economic growth as well from resource use. That's the environmental impact. And so if you look at it and dig in a little deeper, one of the things you find is, and it's talked about in the report was actually chaired, or the panel was chaired by a man by the name of Hans Brunick. He came and spoke at our conference last month in April and had a long discussion about that. But if you look at Western Europe and you look at the United States, we're considered highly developed economies, but we also consume 10 times more material than low-income countries. So we have to find a way to do that absolute decoupling where we reduce our resource consumption relative to the Sustainable Development Goals that the UN has. We've got to find a way to allow the developing world to grow and improve well-being while at the same time having a relative decoupling, so not consuming materials as fast as they are growing. And then that impact decoupling, which everybody needs to focus on. So that's kind of the global picture. Let's look at the United States for a minute. So the REMADE Institute is a Manufacturing USA Institute. So there's 17 Manufacturing USA Institutes. DOE oversees 7 of them. And all of the ones that DOE oversees focus on reducing energy and emissions in manufacturing. So this is some data that came out of the Industrial Decarbonization Roadmap that was released a couple of years ago. And you can see that the industrial sector is responsible for the majority of energy-related consumption or energy use, as well as emissions. And if you further break that down and look at only manufacturing, which is only one component of the industrial sectors, the others being agriculture, construction, and mining, as a whole, manufacturing consumes 25% of the energy in the United States and is responsible for 25% of the emissions. So that's why this matters, the work that we're doing at the REMADE Institute and the other Manufacturing USA Institutes. So REMADE was established in 2017. It was completed in 2016, but our focus is really on reducing embodied energy and carbon emissions through applied research and development. And the way we do that is in a few ways. So one of the ways to reduce energy and emissions is to go from using primary materials or virgin feedstocks to using secondary materials. Aluminum is a great example. It takes 20 times less energy to recycle aluminum than it does to produce aluminum or virgin aluminum. So if we can transition from using primary feedstocks to secondary feedstocks, we can reduce energy and emissions. We also have to be focused on cost and energy parity. So if we can do transition to secondary materials, but we do it at a higher energy and emissions impact, we really haven't accomplished anything. And if it's more expensive than today's incumbent technologies, nobody's going to adopt it. And so it's important that we look at energy and cost parity. The technologies that we're developing, we're not trying to develop them in order to produce great papers. We're really trying to take these technologies and get them out into the U.S. Industrial supply chain, manufacturing and supply chain, so we can increase U.S. economic competitiveness. And of course, EWD is a big focus of all of our institutes, so that as we develop technologies, our workforce is trained and capable of implementing them and using them. I think I mentioned it earlier. REMADE is focused on 4 material classes: metals, polymers, e-scrap, and fibers. So that's where our focus is. And the way we've divided ourselves is really focused on the material life cycle. So let me start with design. So if you look at design, how we design things has a big impact on whether we can disassemble them at end of life, either to remanufacture them and repair them, or to recycle them if need be. Manufacturing is the next node that I want to talk about. And here our focus is really on how do we take these secondary materials that we've produced and actually use them in production, because the reality is secondary materials often come with greater variation in material properties. And so we have to be able to accommodate those variations. A big focus for us is remanufacturing and end-of-life reuse. So again, for those of you who are unfamiliar with the term remanufacturing, in remanufacturing, you're taking a product, which is referred to as a core, and you're returning it to as new or better condition. So you're essentially getting a whole new life out of it, as opposed to, if you're just repairing components or you're just refurbishing it, where you'll get some additional life out of it, but not an entirely new life out of it. And then, of course, recycling and recovery. The last node we have is systems analysis, and that really focuses on looking for opportunities that are cross-cutting to help us understand material flows, help us do techno-economic analysis, and some life cycle assessment to assess the impact of our work. And the metrics that we work and track our projects to are on the right. So again, they're consistent with our goals around feedstock usage, going from primary to secondary feedstocks, reducing embodied energy efficiency and greenhouse gas emissions, finding ways to reuse materials in other industries. So as they say, one man's trash is another man's treasure. So how do we find ways to do that? And then cost and energy parity. What I'd like to do now is just give you an overview of some of the projects that we are working on. I don't have, unfortunately, time to go through all 93 projects that we've either executed or are currently active, or that are soon to launch. But I want to give you a snapshot of the kind of work that we do. And what I've somewhat purposely done is I focused on the stages of the material life cycle that maybe don't get as much coverage. So I may have 1 or 2 examples about recycling, but I want to talk a lot about remanufacturing and end-of-life reuse, systems analysis, and design as well. We are a membership-driven institute, so we've got 167 members, and you can see the breakdown by industry, academic, affiliate organizations like trade associations, as well as national labs. And I know, just looking at the list, there are a number of folks who are on the call right now who have been involved on some of our projects. And so that's been a great collaboration. And I know folks from CMI have been contributed to how we've gotten to where we are. Our current recycling and recovery node lead is Vicki Thompson from Idaho National Labs. Tom Lograsso was at some of our early meetings and helped shape the roadmap. So we owe a lot to the folks on this phone. given the four material classes that we work in, metals, polymers, fibers, and e-waste, we cover a lot of industry sectors, and pretty much you can find opportunities where the work we're doing is impacting each of these sectors. So let me start with systems analysis, and we'll kind of march through the nodes a little bit. So one of the first projects that we initiated was mapping the material base. So Barbara Reck and Tom Gradle from Yale University basically did a material flow analysis for all the materials that Remade focuses on. This is one for the aluminum cycle. This is the US aluminum cycle. We've also done one on global aluminum cycle as well. And if you go to our website, you can actually see animations of all of our material life cycles. So it's not just these numbers that you see in front of you. It's, okay, well, what sectors are these materials being consumed in? Where do they go at end of life and the like? So I encourage you to look at those. As I mentioned earlier, design is crucial because if we're not careful, we can design things in a way that doesn't allow them to be remanufactured or have the material recovered at end of life to be recycled. And, I'll just give you a simple example. Caterpillar, who's one of our members, has a whole remanufacturing business that they remanufacture their products in. And, sometimes having spent 20 years at GE, sometimes design is looking to take out cost, improve reliability, and performance. And, sometimes a design engineer has a good idea. Well, if I just change this geometric feature, I could do, get better performance. But, what happens is if they're not careful and if they're not talking to the remanufacturing side of the house, they could change a dimension that essentially wipes out 10 years of cores that could be remanufactured because there's just not enough material left. So while I'm presenting all of this by node, you can't decouple any of the nodes from any of the other ones because it's all one big whole. So this is a project we've done in solar. We've done a couple projects in solar. One of our first projects in solar looked at how do we build a integrated design tool / lifecycle assessment tool so that we could basically optimize performance and minimize material use. That was led by the University of Pittsburgh. They've got a follow-on project to this, which is really focused on ultimately looking at how do we handle this bow wave of solar panels that's going to come come to their end of the life over the next 10, 15, 20 years. And so what they've tried to do is look at ways to actually look at the whole life cycle, find ways to design economic recycling and recovery facilities, but also estimate the impact. And so if you're familiar with the PV-ICE tool from NREL, the members of NREL are on our team and they're working at upgrading that tool to handle CAD/TEL. So that's a big part of the work that they're doing on the analysis side. But again, ultimately, it's how do we economically find ways to recover materials at the end of their life? I mentioned manufacturing, and while this might look like a recycling project, I'll explain why it's not in a minute. But one of the challenges in aluminum as a whole, I think all of us are familiar with things like recycling aluminum cans, but the aerospace sector has a very low recycling rate relative to other sectors like the consumer products market or automotive. And the problem is you've got alloys in there that make it susceptible to hot tearing and macro segregation if you try to melt the material and then cast it or do other things. And so to solve that, a team from EC Industries and University of Illinois looked at how do we find ways to, using a modeling approach, turn this scrap aerospace aluminum into high-value structural castings for the automotive industry. And you can see the high level, what they did. They did some analysis early on. They looked at, of course, what the starting compositions that they were going to be dealing with. So they had a sense of where they were going. They did some assessments and validated their modeling tools. And then, took that up to pilot scale, did material properties. And by the end of 18 months, they were able to go from a concept of how they thought they might do recycle this material to actually casting this engine block. And it was cast and inspected, had no defects in it. So again, part of what we're trying to do is most of our projects are 2 years or less. And so we're trying to accelerate getting the products out, getting the results of our research out into industry as fast as possible. And this is just one example. And again, the reason why it's in manufacturing is because, again, you're going to see some variation based on the incoming scrap, based on how the material is processed. And so finding ways to be able to reuse this secondary feedstock in manufacturing is why it was classified as a manufacturing project. So what I thought I would do to cover some of the other nodes that we've got is to talk about the e-scrap portfolio and materials. So, we've got projects that are focused on portable consumer electronics, where we're trying to recover material from printed circuit boards or industrial electronics, where we're trying to find ways to remanufacture those circuit boards. So that's some of our focus, and you can see some of the materials we deal with. We've gotten into EV batteries quite a bit. Again, not from a standpoint of we're trying to focus on recycling EV batteries or EV battery materials. It's much more focused on remanufacturing and reuse and disassembly in an automated fashion. I talked to you a little bit about photovoltaics. So in addition to the design project, we've also got a project to recover a number of the materials in solar panels, and I've given you a list there. So let me just kind of walk through these projects just to give you, again, a sense of where we're at. So systems analysis for e-scrap. One of our teams, actually from INL, worked with an e-scrap recycler, Sun King, to look at a decision support framework. So I think they took a biofeedstock tool that was looking at biofeedstock and converted it into how do we optimize recovery of e-scrap. So Sun King drives to various suppliers of e-scrap and collects things. So how do they do that most efficiently? How do they map out where they go, which day, and what's the economics of it? How does the process that they use to actually do the recycling impact economics? So they built a tool to do that. We've also got work in remanufacturing on condition assessment of used electronics. So in remanufacturing, what often happens is they do functional tests on electronics. So, do I have the right voltage here? Do I have the right resistance across this section of my circuit board? And that's how they test boards, whether to put them in or not. But what we're trying to do is find latent defects. So if we know and could identify latent defects before they occur, then potentially we can find ways to reuse more of those printed circuit boards. And so this is a project done with a company by the name of Centric Solutions. They deal with remanufacturing of consumer product electronics. And again, this has been demonstrated. It's actually on their factory floor right now being used. There's a project here that I think Subodh's still on this call, but he worked with a team at Virginia Tech, and they worked on this game technology to be able to try to recover aluminum, silver, platinum, and palladium from PCBs. The technologies, Phoenix, Subodh's companies actually licensed that technology. So I've got a couple of projects related to batteries. And so just one of the things, I was at the Recycled Materials Association conference last month. And one of the sessions they had was focused on, battery recycling and handling batteries and the dangers of that. And the person who leads that class said, if you want to become an apprentice electrician, you have to do an apprenticeship for 4 years. You go through a lot of testing and teaching hands-on before you're allowed to get your apprentice license. If you want to work on recycling or recovering batteries, you don't need to go to any courses. And of course, then they proceeded to show us a lot of videos of batteries being punctured and exploding and all the dangers associated with that. So they're trying to work on helping deal with safety aspects of batteries. But one of the things that we've worked on is how do we diagnose batteries very rapidly? So instead of taking 2 hours, how can we do the diagnostics in less than 5 minutes? So we've got a couple of companies, commercial companies working on that. We're also looking at automated ways, automation of remanufacturing of battery modules. This is a project with Big Battery, who repurposes end-of-life batteries. So they take, once you get to 70 or 80%, they'll take those modules, they'll put them into other applications to repurpose them. And a big cost is how do you disassemble and automate that process. So that's their focus there. And then a project we're going to be launching here in a few months is, again, using machine learning and some diagnostic technologies that the company has done for nickel metal hydride batteries and applying that to lithium-ion batteries to enable them to rapidly assess the capability for reuse of those modules. So again, you can see from some of these projects a lot of the work that we do around keeping materials and products in use. Here's some other technologies, just in the interest of time. I'm not going to walk through all of them. I talked about some of them. We've got ones in design. I talked about condition assessment and some of the battery technologies, but we're also looking at how do we inspect rapidly and evaluate products or cores when they come back. So kind of the process is when a core comes back, it gets disassembled. Each of the parts gets cleaned and then inspected. And what you'd like to do ideally is, because much of current remanufacturing is manual labor, which is expensive, including the disassembly and the cleaning, is you'd like to find ways to assess things automatically without having to actually take things apart and put a lot of labor into it, only to find that the core doesn't have much residual value. So again, whether it deals with technologies like that or technologies dealing with information flow or taking cost out by taking labor out, there's a lot of work that we're doing to increase remanufacturing intensity. The last project I think I have is really a project that ASU and First Solar are doing with TG Recycling. Again, they're trying to find ways to recover silver and lead from these, as well as silicon from these solar cells. And this is just some information about what they've been able to achieve. They're trying to get to 95% recovery of silver and 99% recovery of lead. As I mentioned in the beginning, one of the things we have is we have these performance metrics about energy and emissions reductions, primary material consumption reductions. And so what we do with every project is we track its impact, and we actually ask teams as part of their proposals to tell us what the impact is in terms of material usage, in terms of energy reduction or emission. And so we set out targets at the beginning of our of the Institute. You can see what those targets are relative to emissions and material consumption, energy consumption. And what you can see is through the portfolio that we have now, we're well on track. I accidentally pulled an old one, but we've hit 100% for each of these metrics with the portfolio we have. So we have the potential to hit the goals we laid out initially when we started the Institute. I talked about enabling technologies again. We're trying to get this technology out there. A lot of our focus of late has been on tech maturation and demonstration, either taking previous technologies that had been demonstrated or developed under REMADE funding and maturing those, finding ways to take technologies that other companies have developed and mature those to TRL 6, TRL 7. So that's been a big focus. Again, we've got 3 licenses. We've got the license with Phoenix on the recovering metals from printed circuit boards. Ohio State has a project that they've licensed the technology for going to entirely the use of secondary aluminum in the die casting industry, and they've licensed that technology to Audubon Metals. And then Phoenix has also licensed some of the technology that came out of one of their projects for secondary aluminum. So we are starting to license our technology, and so that's exciting. And then just going forward, and I think this is my last slide, is one of the things we're trying to do is we've got these big initiatives, we're calling them. So as I mentioned, 93 technology related projects that we've funded or in various stages of being funded. And we're trying to combine those. The sum is bigger than of the parts is, or the whole is bigger than the sum of the parts. And so we're trying to combine the technologies we've done in each of these initiatives, whether it's MRF Next Gen or full EV recyclability, in a way that we form a portfolio that allows us to attack the entire supply chain and end-to-end supply chain for all of these to enable us to continue to drive impact for U.S. manufacturing. So with that, I'm going to stop and I will open it up to any questions that folks have.
Looks like we do have a couple of questions, but before we get started on questions, I want to thank you again for Magdi, for a great presentation and the view that you've given us on REMADE's portfolio. And I think many people online right now are thinking about possibilities, how we can even work with REMADE in the future. We have so many overlapping areas, as you know, and we've done CMI projects with REMADE in the past. So many of the researchers will be excited about asking you some more about in-depth, probably questions about some of the work that you're doing currently. We loved the system analysis piece, the remanufacturing and reuse, and recycling and recovery. Those are all areas that we kind of overlap in different ways. So while we're waiting for additional questions, why don't you go ahead and start answering the current questions? And thank you again for a great presentation.
Thank you, Cynthia. So one of the questions is, does Harvard listing of rare earth elements from fly ash and our phosphoric clays have a role in the circular system? It may, but as far as we're concerned, we're not working on those kind of projects relative to things involving recovery of materials from fly ash. In part because, again, a big focus for us is e-scrap. And if you look at the concentration of many of these materials in printed circuit boards, the concentration is much higher if you can recover them from printed circuit boards than if you can recover them from fly ash or mining tailings and the like. So that's not a focus. Can we share the slides is another question that came up. This, as Cynthia mentioned, this will be posted, I think, in a week or two. And so you'll be able to see the slides there. Any other questions that folks have?
While we're waiting for some questions, and I'm thinking some of our recycling folks might have some out there. Is there anything else that you would like to add with regard to the ease of working with Remade, or what in particular you're looking for?
Yeah, so we try to be as easy to work with as possible. The fact that we continue to grow, I think in the last couple of years, we've grown 60 or 70%. So we're always looking for new members who have expertise that's relevant to the things that we do. Um, and particularly from companies. But again, you saw how many universities we have. I think we have more national labs on our team than any other manufacturing USA institute. So we're always looking for collaborators with great ideas who can help us accelerate the transition to a circular economy.
It looks like another
Uh,
question has been added.
yeah, regarding meeting the institute's goals, did you say you compiled from projects self-declared goals? Um, Thanks for the question, Ruby. It's nice to see you um, online. I'm going to answer what I think is the question. So, um, as I said during my presentation, we ask all the project teams to tell us what the impact of their project is going to be potentially if they're successful at the beginning of the project. We also realize that there are and very few of them are life cycle analysis experts. So what we did is we created a simple calculator. It's an Excel-based calculator that's really based on the differences in embodied energy and emissions between primary and secondary feedstock to allow people who don't have that expertise to, to predict what the impact of their projects are. We go through and we scrub them and make sure that they make sense. We had an early project that essentially claimed it was going to recycle all of the aluminum consumed every year in the United States. That was a little bit aggressive, but it was going to have some big impact. So we validate those technologies or those impacts ourselves. And then at the end of the project, based on how successful they have been, or maybe that they didn't reach their goals, we'll recalculate those benefits. So it's an ongoing process. And as you saw from some of what I presented, some of the projects actually have life cycle assessments as part of their scope of work. In general, our projects starting at around TRL 3 or 4. So they're starting across the range, of TRLs. When we first started, we had what we called exploratory projects. So exploratory projects could have been as low as TRL2, where it was somebody had a really good, what they thought was a good idea for a project, but it had some significant risk. So we gave them a year and a couple $100,000 to try to reduce that risk. If they were successful, they could come back and apply for follow-on funding. So, we had some projects that are lower TRLs. Again, our goal is to move it to 6 and 7 so that we actually demonstrate so industry is willing to invest. But we have them across the whole range of starting TRLs.
We do have a little bit more time for a couple of questions. Again, while we're waiting to see if any questions get put in the queue, Magdi, do you have any other comments about how to contact you and, or with the project, or what your process might be?
Sure. So you can see here on the screen, there's my email address. I would love to have you reach out and contact me. Depending on the subject, I may refer you to one of the project managers who has a deeper expertise in that conversation, but we can certainly set up a meeting. I also have on emails that I send at the bottom of my email, there's a button that says schedule a meeting. If you click on that, it will automatically show you open slots I've got so that, we minimize the going back and forth. But again, I welcome the chance to to talk with the teams and individuals here about potential opportunities.
Okay, again, we have a little bit of time for a question. We'll see if another one comes in, but I want to thank everyone on this webinar for attending. The recording is going to be available next week at aimslab.gov/CMI, and again on our Critical Materials Innovation Hub YouTube channel. So please find it in either of those places. We would love to have you join us again for the next webinar on June 25th to learn about the IEA Global Critical Minerals Outlook 2024, presented by the IEA Senior Energy Analyst, Tae-Yoon Kim. We always have this information in the Critical Times. We always have it posted many different places. So please plan on joining us. As I mentioned before, if you have a suggestion for another webinar or topic presenter, please share it on the exit survey. And we're always looking for something that will, again, meet the needs of our CMI family. I want to, doesn't look like we have any additional questions, but again, Dr. Magdi Azer, thank you again for your presentation and being with us today.
Thanks for the invitation, Cindy.
You are welcome. Thanks, everybody. We hope to see you next month.